So we're going to continue with this lesson in 7.1 and 7.2, and we're going to look at how exponential functions can be used to model very real-day, real-life activity, both growth and decay. Let's look at an example. We go to the bank, we deposit $500 into a bank account. It earns 5% every year. I want to write a function that describes the balance, how much money I have in the bank after T years. So I earn interest every year, and then I earn interest on top of that interest that I earn. So let's just look at how that works. In the first year, or let's create a table. We have time and our balance. And in the first year, we deposit our money. We have $500 in the bank. After 1 year, we have the $500 plus we have the interest that we earned. The interest is going to be $500 times 5% in this case, so that's going to be 0.05. Now we could simplify this. This is actually equal to 1.05 times $500. Or actually, let me rewrite that. I'm going to write it like this. $500 times 1.05. And we could do that because we can think of it in invisible 1 here. 1 plus 0.05 is 1.05. Okay, second year. Whatever our previous balance was, that's how much we have in the bank. So we have $500 times 1.05. And now we earned interest on that amount. So now we have $500 times 1.05. That's how much we had in the bank at the end of the first year. And now we earn 5% interest on that. So let me just highlight the interest portion here. Now this is then equal to, if I were to combine this, I have this common factor right here. So I have 500 times 1.05 times another 1.05. So if I can imagine this imaginary 1 right in here times 0.0 or plus 0.05 here, then I have 1.05 again. So I could rewrite this like this: 500 times 1.05 squared. So you can see this kind of progression. I started with $500. Let me do that in another color. I started with $500. Then at the end of the first year, I had $500 times 1.05 raised to the first power. Then at the end of the second year, I had $500 times 1.05 raised to the second power. And we could keep on doing this, and we would just see that this exponent just keeps increasing by 1 for every, basically it's the time value. I have 1 here, and I have an exponent of 1 there. I have a 2 here, and I have an exponent of 2 here. This suggests an exponential type of growth. And that's precisely what we see here. So let's go to the next page. It's farther in your notes. We actually have what we call a growth model. This is an exponential function, and in this case the variable is t. We have the function y as as t varies. In this case, we have a, which is the initial amount that we start with. We have r, which is the growth rate. And we have t, which is the time. This is how much time expires. A decay model is exactly the same case, but instead of adding, we have a subtraction. We have a decay rate instead. Let's look at this example one more time. In the case we deposit $500, 5% yearly, write a function describing the balance after t years. So to do that, we say f of t is equal to, we have the initial amount of money that we put into the bank, $500, and that's our A value right here, the initial amount. We have the growth rate, which is 0.05, 5% yearly, so we put 5% here. And that's the value of R, which is our growth rate over here. And then we have T, which is our time. That's our variable in our equation. Our function, f of t, this is our balance, is equal to the initial amount, $500, plus 1.05 raised to the t power. Now there's a little twist on this. Suppose we want to compound the interest at a faster rate. So in this example above, we're earning interest 5% every year. Suppose instead we have this case, what we call compounded interest. We start with the principal amount, the amount P, and we have an annual rate of earning interest, but we earn interest maybe instead of once a year, we earn it every 4 times a year, maybe 10 times a year, maybe even daily. So what we call this is, that's what we call this being compounded n times a year. So there's an annual rate of interest, maybe 5% is the annual rate of interest, but we say n is 5, every 1/5 of a year we earn 1% interest, and that piles on top of each other. So in this example here, we have a principal of $1,000 that we start with, earning interest at 4%, a balance or compounded 4 times a year. If we create all of our variables, we have our principal as 1,000. We're compounding 4 times a year. That's n is equal to 4. We have our interest rate of 4%, just happens to be the same number, but it's a different value, 4%. And we can plug these things into our equation. And after 1 year, we find out that we have earned $1,040.60. If we had just compounded 1 time a year, just 1 time at the end of the year, we would have had 1,000 plus 1,000 times 0.404%, and that would be equal to $1,040. So you can see there is a slight difference. If we compound 4 times a year, we will earn slightly more. There's a problem right at the very end. What happens if you were to compound daily? That would be a case where n is equal to 365. That's something you can do. You could see how much more would you make if you compounded daily instead of compounding 4 times a year versus compounding 1 time a year at the very end of the year. So why don't you give it a try, see what you get.